much. I will talk about high-eccentricity clouds and stars near supermassive black hole. This work was done under collaboration with Vladimir Karas and Andreas Eckart. So, first I will introduce and talk about some basic conditions near the galactic center and characteristics of motion. Then I will also talk about gas and dust interaction, summarize our results, and that will be followed by discussion and conclusions. So, as you probably all know, supermassive black holes reside in most galaxies, and their masses are in a range from a million solar masses up to billion. And Sagittarius A star is very important because it's the nearest example of nucleus to us, and it may be considered as a paradigm of low luminosity nuclei. That means that the accretion rate is well below the critical Eddington accretion rate, and the accretion flow is generally considered to be relatively inefficient, and the character of this flow is clumpy, which was recently discussed in the work by Cherny et al. And it is surrounded by gas and dust clouds and nuclear star cluster, and these components interact with each other. Recently, as you also, many of you have probably noticed, an infrared access source, also named G2DSO, has been discovered. It was first mentioned by Gillesen et al. 2012, but also followed by Eckart 2013 and Pfeiffer. Here the orbit is plotted on the sky plane alongside with other stars belonging to S cluster, which is more or less isotropic, and these are the shortest period stars S2 and S102. So the orbit is very eccentric of this cloud, and it is expected to reach the pericenter around this time. There is some uncertainty. So in some works based on the orbital elements, it was determined or approximated to be early 2014. In others it was already September 2013. But basically it's not important for some discussion of physical processes connected to it. So motivation for our work was its unknown origin. Some ideas, although have been suggested, and unclear structure. Some claim, mainly Gillesen, that it's coreless cloud. Others that there should be star embedded. And the aims of our work were models of pericenter passages with the involvement of hydrodynamic drag due to ambient medium, radially directed wind outflowing from the center as well as from the star, and the bow shock region that may form near the pericenter. Then we also asked under what conditions these encounters can lead to periods of enhanced accretion activity, and what is the difference between Gaussian and Keplerian distributions, and also what is the effect of wind and bow shock. So here are the illustrations of considered scenarios. So this is coreless cloud with gaseous and dust component. This is with star embedded and bow shock at the front. And this is also a scenario that we put forward, and at this stage, it is still possible that there may be also another star, so it can be a binary system with a common envelope. So in our simulations, we used these density profiles, the semi-analytical relations for electron temperature and density, derived by Broderick and Lab. And when we compute the characteristic Keplerian velocity with the sound speed, we see that for distances less than million Schwarzschild radii, the motion is mostly supersonic. Then in our model we included hydrodynamic drag, and due to supersonic motion it may be basically treated with Stokes relation, which is proportional to some effective cross-section of particles to density of ambient medium and the square of relative velocity with respect to ambient medium. And when we compare the ratio of the acceleration due to drag and gravitational acceleration, we see that it is in general not negligible and should be included in models, although there is a large span of values depending on the cross-section of dust grains. It is also important to discuss gas and dust interaction. In interstellar medium, typical gas to dust ratio is about 100, and it was recently reported by Sherbakov that expected relative dust abundance for G2 DSO is about 0.65. Gas and dust component may be both weakly and strongly coupled depending on conditions, and this is expressed by Coulomb coupling parameter, which is proportional to the cube of electron density and inversely proportional to temperature. So, and this mutual coupling in the complex plasma, including viscous forces, increases the effective dust grain mass. Another process that may occur is the sublimation of dust grains near the center, and this is simple relation. For example, in Barwines 87, where temperature of dust, equilibrium temperature, is function of luminosity and distance and optical depth, and we can simply derive the sublimation radius. And when we plot in this coded plot temperature as the function of optical depth and radius for pericenter distance for G2, we see that the dust is probably not going to totally evaporate, since the isotherm 1500 kelvins, like approximately the evaporation temperature for dust is here. Here are test runs for single particle. This is for no drag included, and when we include the drag, basically the semi-major axis and eccentricity decreases, and particles spiral towards supermassive black hole. Then we discuss also the role of central star. So here is the run in orbital plane for coreless scenario with Gaussian distribution. So we see that basically the cloud is tidally stretched, and also position the dispersion, velocity dispersion in this in this velocity position diagram, velocity dispersion increases at the pericenter, then it slightly decreases after a pericenter passage and increases again. So then we included the star with 2 solar masses and with Keplerian distribution of velocities for particles, and we see that again the cloud is tidally stretched at the pericenter, and then most of it is torn away after pericenter passage due to hydrodynamic drag. All those small part stays orbiting the star. So this is in position velocity diagram. So again, velocity dispersion increases at pericenter. So in order to somehow simply estimate the number of particles that can be captured, one can compute the Hill radius of the binary system star supermassive black hole, and for typical parameters, in this case it is about 1 astronomical unit. So in combination with hydrodynamic drag, we may expect that if the structure is extended, most of it should be captured and deviate from the original elliptic trajectory. So then we also discussed the effect of wind and bow shock. Mass losing star moving supersonically through interstellar medium forms bow shock, and near the galactic center actually this has been observed and reported by Mužič et al. 2010. And here are some test runs with the varying speed of the wind from the center. So for winds of about 2,800 kilometers per second, dust is blown away. And in our numerical scheme, we included analytic solution by Wilkin 96 with standoff distance, where the pressure of the wind and ambient medium are at balance. And inside the bow shock, we included this density profile, which is proportional to 1 over distance from the star squared. And when we compare the evolution with the wind from the center included, the structure is more stretched to additional non-radial term. So this is the evolution for with the bow shock included for T Tauri star with these parameters. And so again, the cloud is stretched at pericenter, and then some of it starts deviating from the elliptic trajectory, and part of it continues orbiting the star, which may be expected when actually we observed the G2 cloud also contains a star, so a fraction of material should stay around the star. This is for higher velocity of wind from the center, so bow shock then rotates and it's aligned according to relative velocity. And this is an offset between the cloud and a star, which basically the temporal evolution. So this is the first pericenter passage. So first cloud is basically near the star, and after pericenter passage, some part of it is actually detached and torn away from the star, and an offset of about 0.12 arc second may be expected, which possibly can be also observed in near infrared band. So then we also compared the geometry. This is for Gaussian shell around the star with this initial full width at half maximum. So for Gaussian distribution, the cloud is not so affected by the star, and most of it is captured. So this is for this is the evolution and position velocity diagram, and this is for Keplerian disk, which was also discussed in this work by Mary Clay and Lab 2012. And then more particles stay bound to the star, stay orbiting inside the Bow-Shock region. This is in position velocity diagram. So we can summarize the results that from our simulation runs. So coreless clouds should be disrupted, mixed with the ambient medium, and partially accreted. Although it is needed to say at this moment that we just follow the evolution to about 300 Schwarzschild radii, so we do not discuss possible processes also with relativistic effects very close to the black hole. It is more complicated. Clouds containing a star may partially survive and stay orbiting the Sagittarius A star, and significant mass loss is observed basically in all cases for our profiles of ambient medium, so about 90% is captured. And Bow-Shock seems to protect some particles from being captured, which is connected to boundary conditions. However, it is also needed to say that it's 4 parametric space, and it depends on the terminal wind velocity, mass loss rate, and density profiles. So this is in this table is a summary of mass captured. So most of the cloud is always captured, but when the star is involved, about 10% may stay orbiting and follow the original trajectory. So then we also discussed the scenario with a binary embedded in a common envelope. So in our case, we include hot star and possibly a neutron star with 1.4 masses orbiting the star. And here is the plot as we would see the evolution from the Earth. So this is the original trajectory, components orbit common center of mass, and after pericenter they move. So, and in this case, a neutron star is actually ejected from, it moves on a hyperbolic orbit. So, here are also for illustration 2 shortest period stars S2 and recently discussed S102. So this is in PV diagram. So here the velocity, radial velocity of escaping neutron star can be more than 1,000 kilometers per second. And from these temporal evolutions of semi-major axis and eccentricity, the orbit of the primary is actually circularized a little with smaller eccentricity than originally, and here the eccentricity of secondary is above 1, and semi-major axis also decreases for the primary and increases for the secondary. So Then we also discussed, since my master thesis concerns mainly neutron stars near the galactic center, we also discussed possible interaction with these neutron stars. This is a picture or illustration of the process that is expected in galactic nuclei over billions of years, like 10 billions of years, which is an expected age of the bulge, where stellar mass black holes sink inwards due to dynamical friction, and low mass older stars are expelled, so form a shell around the cusp. And here also alongside black holes, neutron stars are expected to exist and to form. And here also inside this central region, young OB stars are observed. So this is also, so this is kind of illustration of what is expected, although it may observations show that there is a slight difference, because in some works, older works, this steep Baikal-Wolf cusp was discussed with steep profile towards the center, and such profile for all the stars has not been observed. Inside the core, the distribution, density distribution seems to be flat. So, but still, it's the interaction with compact remnants is higher. The probability of interaction is higher than in the disk population. So this is the time scale on which these compact remnants are expected to travel towards the core. So for neutron stars, about with the mass of 1.4, the migration radius in 10 billion years is like about 1 parsec, or slightly above 1 parsec. And so when we do some estimates of the population of compact remnants, so white dwarfs, neutron stars, and black holes, so we did some estimates based on initial mass function, and in general the numbers are quite high inside the central region, generally for neutron stars of the order 10 to the 4, 10 to the 5. So for an eccentric cloud like G2 with high eccentricity, we computed this cumulative number of interactions up to the pericenter, and for flat distribution that is now observed for our galaxy, the probability of interacting is quite small. But for a steep cusp, if there was such a Baikal-Wolf cusp, it may basically reach the order of 1 and more. So, but so far nothing has been observed in case of G2 by X-ray satellites, like some accretion or some collisions. So probably we should more discuss these pessimistic scenarios than optimistic. This is an illustration of interactions for steep cusp. So in general, interactions are more probable near the pericenter, where for optimistic scenarios about 3 neutron stars can reside inside the cloud. Then we also analyze the distribution of orbital elements of interacting objects using Monte Carlo approach. So here we can see that mostly low inclination objects with respect to the cloud interact with it, and also with the smaller eccentricities. And here also this is longitude of ascending node and argument of pericenter. And here is the distribution of relative velocities of these interacting neutron stars for apocenter where relative velocities are actually quite small, and if we compute Bondi-Hoyle-Littleton accretion luminosity, so it is about 10 to the 32 ergs per second, so it is close to the Chandra detection limit actually. So, but so far, as I said, nothing has been observed, some high activity. So here is some further discussion. I will maybe just mention that as a possible source of material is minispiral with clumpy streams that can collide, lose angular momentum, and clumps can approach supermassive black holes. So in this sense, G2DSO cloud can be a signature of common mechanism of transporting matter towards the galactic center. And dust in shrouded stars has been before studied by Schubert and Karas in these articles. So maybe I will leave conclusions here, and maybe we can discuss.
So let's take our speaker.